Hello, everyone. In this video, we're going to continue our work in section 8.5, looking at Taylor series and Taylor polynomials. Now, in this video, we're going to just introduce the topic and concept of our error when we use a Taylor polynomial to approximate a function. So let's just take a pause to recall in our previous videos, what we did was we were able to approximate a function value. So just backing up here to example 2. Approximate the value of, say, ln of 1.05 by using these Taylor polynomials. So now the question in our next topic is, well, how close do we get to our actual function value? What's the error between our Taylor polynomial and the function value itself? Okay, so that's all what this next box is about. So we're going to look at this box. There's going to be some abstract notions in here, but we're going to look at the details and more concrete in the next couple of examples. So let's just go through this box together. So this box is dealing with the error approximation for Taylor polynomials, what I just discussed. So in this, or how to compute the error of a Taylor polynomial, let's begin by letting f be our continuous function with n plus 1 derivatives, meaning we can compute the p sub n, or the Taylor polynomial of degree n, for our function f. So let's suppose that Pn is centered at a point A. Now for some number c, we want to know the error that results from approximating our function value at c with our Taylor polynomial of nth degree at c. Well, that error is given to us by the following formula. So this is just notation, e sub n of c is just notation for the difference between the actual function value at c and the nth degree polynomial at c. Okay, so nothing scary so far. This is just notation. But now, still not scary, but we can continue. It can be shown that the value of this error, the magnitude of this error, is less than m, which we'll define here in a moment, times the absolute value of c minus a, so the distance between a and c, to the power of n plus 1, divided by n plus 1 factorial. So just to note here, so recall, so we're looking at our Taylor series centered at A. So then we're looking at some C, maybe C's here, maybe C's here, that's some distance from A. So that magnitude here is C minus A absolute value. I used 2 different examples, but that's what we're getting at. Okay, so now what is M? Well, M is going to be a maximum possible value that the derivative of f can take on the interval from a to c. So I'm going to write that out and then we'll unpack it. So we write the absolute value, whoa, don't know what happened there, the absolute value of the nth degree derivative, or the nth plus 1 derivative, rather, of x is going to be less than or equal to m on the interval from a to c. So I'm going to clean up this picture a little bit over here. Okay, so we're trying to find the error between f of c and our nth degree polynomial, nth degree Taylor polynomial. And so m is a maximum value that the nth plus 1 derivative takes on this interval from a to c. So meaning we can look at, okay, here's our interval from a to c, and our n plus 1 derivative looks like something on that interval, maybe like that. So then m would be the maximum possible value, looks like around here, that n plus 1 derivative of f takes on that interval. Okay, so that was rather abstract because we're just looking at general functions and nth degree polynomials. In the next example, we're going to make this more explicit by looking at specific examples.